Let's talk about parent functions. In grade 11, we talked about a number of parent functions, and it's important in this part of the course for you to know those parent functions, at least at first, their basic behaviors. So let's consider the square root function y equals root x. In grade 11, you learned that there are certain key points on that curve, and the curve looks like this. It's essentially 1/2 of a sideways parabola. You should remember the essential behavior of the function as well as these 3 points that I have listed in red, 0, 0, 1, 1, and 4, 2. The domain of this function is x element of the real such that x is greater than or equal to 0, and the range is y element of the real such that y is greater than or equal to 0. The increasing intervals of this function is x element of the real such that x is greater than or equal to 0, or x is an element of 0 to infinity. 0 has a square bracket, infinity has a round bracket. Generally speaking, when we do intervals of increase or decrease, we put them in interval notation. That's the usual way. Decreasing intervals, there are none. The function is not even, because if it was even, then it would reflect on itself, which it clearly doesn't. And the function is not odd, because if we rotate it 180 degrees about the origin, it does not fall back onto itself. There is no end behavior as x goes to negative infinity. So this is one of those rare cases where when we ask for end behavior, you can only really state it in one direction. As x goes to infinity, y goes to infinity. The curve will become infinitely high and the y values will become infinitely large as x goes to infinity. Now let's talk about the absolute value function. Remember that the absolute value of a number is the distance of that number from 0. And we show we're evaluating the absolute value by putting the number inside absolute value bars. In other words, we show we're evaluating the absolute value of 6 by writing 6 in those absolute value bars. So for example, the absolute value of 8 is 8 because 8 is 8 units from 0. Imagine a number line. There's 0 and there's the number 8. Well, 8 is 8 units away from 0. And similarly, the absolute value of negative 8 is 8, because if you look at negative 8 on that same number line, it is also 8 units away from 0. Now let's make a table of values of the function y equals absolute value of x. We see that we get these points. And when we graph those points and recall the behavior of the function, it looks like this. It's important when you ultimately graph this function with transformations to recall the basic behavior of the function and recall the 3 points that we've listed right there. The domain is all real numbers. In other words, there is no real number that you cannot put in for the number x, for the variable x right there. The range, as you can see from the graph, is all values of y greater than or equal to 0. Now, the increasing interval is all values from 0 to infinity. We can put a round bracket on 0. Personally, I think a square bracket's more appropriate, but either way, you must have a round bracket on the infinity. That's the increasing interval. The decreasing interval is all x values less than 0. In other words, if x is any value in between negative infinity and 0, you're in a decreasing interval. And remember, don't look at that arrow. That's not telling you that it's increasing. That's just helping you understand the behavior of the graph. However, to determine if something is increasing or decreasing, what you do, recall that you want to go to a point on the interval, take a minuscule step to the right and ask yourself, do you go up or down? And if you go down when you take a minuscule step to the right, you're in a decreasing interval. Symmetry, this is an even function because it reflects upon itself in the y-axis. In other words, it's symmetric about the y-axis. As x goes to negative infinity, y is shooting towards positive infinity, and as x goes to positive infinity, y is also shooting towards positive infinity. There's our end behavior. Now let's talk about the cubic function. We can make a table of values of this function, and if we do, we have these values right here. Now, when we, actually there's some errors here. When x is -3, -3 quantity cubed is the same as -3 times -3 times -3. So that actually equals -27. So anyways, we have the values here as I've modified. And when we graph those on a curve, we see that on a Cartesian plane, we see the general behavior of the function. Now, we did not include the points -3, -27, and 327 in the graph I just showed you because we have to save room. And although it may not be obvious, this curve is actually infinitely wide to the left and right. Any x value to the far left or to the far right can be inputted into that function. And so what we want to remember is the basic behavior as we've shown there, as well as the three key points of -1, -1, 0, 0, and 1, 1. The domain of this function is all real numbers, and the range is all real numbers. And the increasing interval is all values from -infinity to infinity. Any x value between -infinity and infinity, if you insert it to the equation of the function, you'll end up at a point on the curve. If you then take a minuscule step to the right, you'll go up. Again, do not pay attention to the direction of that arrow. That's not telling you it's a decreasing function. That's just telling you where the points are. Remember, to be an increasing or decreasing interval, you're taking a step to the right, no matter where the direction of the arrows are in the function. Symmetry, this is an odd function because it has rotational symmetry about the origin. This red portion, if I rotate it 180 degrees, will fall exactly on the other side. End behaviors, as x goes to -infinity, so as x goes this way to the far left, y is going down. And as x goes to the far right, y is going up. So our end behaviors are as listed there. The reciprocal function. This is an interesting one because this curve has two asymptotes. An asymptote is a line that a curve approaches and gets infinitely close to but never touches. This particular curve has both a horizontal asymptote, the x-axis with the equation y = 0, and a vertical asymptote, the y-axis with an equation of x = 0. Now when we graph the curve, it looks like this. If we want to establish why it looks like that, we can plug in many different values for x and many different values for y. And if we plot all those points, we will see that this is ultimately the behavior of the function. Now, a few things are noticeable. The larger in magnitude the x value gets, whether positive or negative, the closer to 0 the y value gets, but the y value will never equal 0. Graphically, this means that as the function's x values get closer to -infinity or infinity, the y value will get closer to 0, but the y value will never equal 0. This means that the line y = 0, i.e. the x-axis, is a line that the curve will approach but never touch. It is an asymptote, i.e. a horizontal asymptote. The x value can never be 0 because that would make the denominator 0. Remember, the function is y = 1 over x. If I let x = 0, the denominator is 0. We can't allow that. So that means the x value can get infinitely close to 0 from either the left or the right. The line x = 0 ends up being a vertical asymptote. The larger in magnitude the x values get, the smaller in magnitude the y values get. The smaller in magnitude the x values get, the larger in magnitude the y values get. So putting all those ideas together, we get the curve that we showed you here. This is the parent function. And it's important to remember the basic behavior of the function as well as 2 points, -1, and 1, 1, and also know the horizontal asymptote y equals 0 and the vertical asymptote x equals 0. Now, our domain and range, our domain is x less than 0, x greater than 0, or kind of a clever way of expressing that is just saying x is a real number such that x doesn't equal 0. Our range is y less than 0, y greater than 0. Equivalently, we can write our range this way. Now, our increasing intervals, we have none. There's no point on this curve where if you took an infinitely small step to the right, you would go up. However, our decreasing intervals, we have actually 2 of them. This is a decreasing interval because anywhere on there, if I take a step to the right, I go down. And similarly, the portion on the right-hand side above the x-axis, that is also a decreasing interval. So if I state that in interval notation, I can say -infinity to 0 in union with 0 to infinity. Now, we do not say -infinity to infinity is a decreasing interval because at x equals 0, there is no point. And so therefore, we can't say x equals 0 is part of a decreasing interval. So it would be wrong to write that. Symmetry. This is an odd function because it has rotational symmetry about the origin. If we rotate that curve 180 degrees around the origin, it will fall back onto itself. As x goes to -infinity, y gets infinitely close to 0. So as x goes far to the left, y keeps getting closer to 0. And as x goes far to the right, y keeps getting closer to 0. So our end behaviors are as written. Now let's talk about the exponential function y equals 2 to the x. It's important to recall this from last year. And y equals 2 to the x looks like this. The farther we go to the left, the smaller the y value becomes. However, the y value will never be 0. The x-axis is a horizontal asymptote. So our domain is x is an element of the reals. Our range is y is an element of the reals such that y is greater than 0. Our increasing interval is all real numbers. We usually put increasing intervals in interval notation as I indicated. There is no decreasing interval to this function. This function is neither even nor odd. It does not reflect exactly upon itself in the y-axis, and if we were to rotate it 180 degrees about the origin, we'd end up with a curve below the x-axis. It definitely is not rotationally symmetric about the origin, so it is not odd. The end behaviors, as x goes to -infinity, y goes to 0. As we go far to the left, y gets closer and closer to 0. And as we go far to the right, y gets infinitely high, so y goes to infinity. Now, the exponential function 3 to the x is very, very similar to 2 to the x in a lot of ways. Different values, but a lot of the same general behavior. The farther we go to the left, the smaller the y value becomes, but it will never be 0. Y equals 0 is a horizontal asymptote. Our domain and range are the same as they were for 2 to the x. And our increasing interval is the same, and we have no decreasing interval. For the same reasons, the function is neither even nor odd, and we have the same end behaviors we had for the function 2 to the x. Now let's look at the exponential function y equals 1/2 to the x. We could make a table of values if we wanted, and if we do that, we get the curve as shown right there. The farther we go to the right, the smaller the y value becomes, but it will never be 0, so the x-axis is a horizontal asymptote. The domain is all real numbers. The range is all real numbers greater than 0. Now here's where it gets a little different. There's no increasing interval like there was for the other 2 exponential functions. Rather, it's all decreasing. As we take a minuscule step to the right, we'll be going down at all times. So the interval notation description of the decreasing interval is x element of -infinity to infinity. The function's neither even nor odd. As x goes to -infinity, y shoots up to positive infinity, and as x goes to infinity, y shoots to 0. We can look at the exponential function y equals 1/3 to the x. Looking at that, we would come up with the table of values that we have shown. The function looks similar to 1/2 to the x, but it's a little steeper. The farther we go to the right, the smaller the y value becomes, but it will never be 0. The x-axis is a horizontal asymptote, and so we get the domain and range as shown right there. There's no increasing interval, and the decreasing interval is all values between -infinity and infinity, for similar reasons as we had for the last exponential function we just looked at. The function's neither even nor odd. It's not symmetric about the y-axis, and it's not rotationally symmetric about the origin. And just like the function y equals 1/2 to the x, the end behaviors are as x goes to -infinity, y goes to infinity, and as x goes to infinity, y goes to 0. Now, let's recall a couple of trig functions. The sine curve. The curve y equals sine x has the following points in degree mode, and it looks like this. Of course, that's only one cycle of the periodic function. The function actually goes infinitely in both directions. Recall from grade 11 that the amplitude is 1. Amplitude is a measure of the height from the axis of symmetry to the highest point. So that's 1. Or you could say from the axis of symmetry to the lowest point. That's 1 as well. The axis of symmetry is the straight line that the function is going equally above and below. The phase shift is 0 because that indicates how far from the origin we moved. Well, the parent function starts at the origin, so the phase shift is 0. And the period is 360 degrees. A period is the horizontal length of one complete cycle. So in other words, how long is it horizontally to complete one cycle? And we see there that the period is 360 degrees. In radian mode, it's very similar. We just convert to radians using the idea that 180 degrees is equal to pi radians. Now, we are going to have an extensive trigonometry unit later in the course, but right now we're talking basics here. Now, that's only one cycle of the periodic function, but you might recall from grade 11 that similar to what we just said, the amplitude is 1, the axis of symmetry is at y equals 0, the phase shift is 0, and the period is 2 pi. Now, the domain is x element of the reals because any real number can be plugged in for the angle of a sine x curve. The range is all values between -1 and +1. Now, we're going to take a look at what this curve looks like when we actually extend it out in both directions. The curve y equals sine x looks like this. And it goes on infinitely to the left and infinitely to the right. Okay, many different periods. Now, if I said to you, what are the increasing intervals of this curve, you'd say, okay, well, it goes from an x value of -90 degrees to an x value of 90. And then it goes from an x value of 270 to an x value of 450. And it goes from an x value of 630 to an x value of 810, just like we've written here. Or if you prefer to not say, instead of saying -90 less than or equal to x less than or equal to 90, as we discussed in one of our other slides, you can say -90 degrees less than x less than 90 degrees. I actually prefer that you put the equal sign in there because I think the definition supports that. But your textbook says does not include the equal sign, so the textbook only says less than, so I'll accept either. But anyways, we could say that those are the increasing intervals. And by giving 3 of them, we're saying there's a pattern going on here. And by putting dots on the far left and dots on the far right, the way we've done here, we're indicating that it goes infinitely in both directions. And we're saying to the reader, look at the pattern and you'll figure out what I'm trying to express. But if you really want to get sophisticated, we can say it more formally this way. We can say, for instance, let's take the interval 270 to 450. We can say that this, if I let k equal 4, then 270 degrees is 4 minus 1 times 90. So again, I'm letting k equal 4. K minus 1 would be 3. 3 times 90 degrees is less than or equal to x is less than 4 plus 1, which is 5 times 90 degrees, which would equal 450 degrees. And I'm saying k over 4 must be an element of the integers. If I take that k value of 4 and divide it by 4, I get the number 1, and number 1 is an integer. Okay, number 1 is an element. When you see a z written like that, that means the set of all integers. This is a very sophisticated way of writing it, and for those of you who are in computer science, you might really kind of enjoy that. It's kind of like coding in a way. Now, so again, just to tell you, the end of this statement is saying that if we divide k by 4, we have an integer. This is another way of saying k is divisible by 4. So letting k be negative 4 over 4 would give us negative 90 degrees less than or equal to x less than or equal to 90 degrees. And then letting k be 0, because 0 over 4 is an integer, would give us, actually letting k be negative 4 would give us negative 450. Sorry. Letting k be negative 4 would give us negative 450 less than or equal to x less than or equal to negative 270 if we were to let k be 4 and apply this formula. And so this is an accurate way of describing all of the different intervals. And so this is an explanation of that. Letting k be negative 4, we would get that interval right there. Letting k be 0 would give us this interval. Letting k be 4 would give us that interval. We could similarly replace the less than or equal to signs with less than signs. Or in interval notation, we could state it either of these ways. Or if we wanted to do it the more formal way in interval notation, we could write it this way. We could obviously put all of those previous intervals into radian mode by converting all degree measures with radian measures. And you would be replacing 90 degrees with pi over 2 in all of those formal descriptions. Similarly, we would have decreasing intervals. And we could write the decreasing intervals the same way we wrote the increasing intervals, using the same philosophy of putting 3 dots on the far left, 3 dots on the far right, showing 3 of the intervals to let the reader establish the pattern, and then leaving it up to the reader to figure out the rest. We could put less than or equal to signs in those decreasing intervals, which I prefer, or we could just put less than signs. We could state it more formally the way I have here. And again, what we're saying here is k over 4 is an integer, which means k is a number divisible by 4. And so we're saying as long as we let k be a number divisible by 4, this formula that we're writing out here will always produce a decreasing interval in this case. Okay? So moving on then, using k values of negative 4, 0, and 4, we would get intervals as shown. And we would be able to say, again, this is a more formal way of doing it. People who are into computer science might enjoy the coding aspect of this. It's kind of neat, I think. We could replace the less than or equal to signs with the less than signs based on me telling you earlier that the textbook uses a different definition of increasing and decreasing than I do. And in interval notation, we could write we could write the decreasing intervals this way. Okay? Now we could put all those previous intervals into radian mode, and we'd be able to convert all the degree measures with radian measures. What we would have to do there is replace 90 degrees with pi over 2 in all the formal descriptions. Now, here's something that's interesting. This is an odd function. Believe it or not, if I take any point on this curve and I rotate it 180 degrees about the origin, I end up right back on an associated point. If any point, it'll happen. If I take the curve as a whole and rotate it 180 degrees about the origin, it falls back onto itself. So what that means is that the function y equals sine x is an odd function. Now, the periodic function varies between -1 and 1 infinitely in both directions, so there are no discernible end behaviors. Now, let's look at the function y equals cos x. Sure, this word right here, I should say cos, but we're looking at the cos curve, y equals cos x, and it follows a very similar process. We know the basic idea of the curve. We recall from grade 11 what our amplitude, axis of symmetry, phase shift, and period are. We could also put it into radian mode, and we would know what our amplitude, axis of symmetry, phase shift, and period are. We will do an extensive unit on trigonometry later, so for right now, we're just talking about the basics. The domain and range are as shown. Now, to determine the increasing and decreasing intervals, we show many intervals of the function. We know it goes infinitely to the left or right. And to show the increasing or decreasing intervals in a relatively simple way, we could write it out like this. And we're just showing from -540 to 360, we have an increasing interval. From an x value of -180 to an x value of 0, we have another increasing interval, and so on and so on. It's important to show 3 of those intervals in the statement right here. It's important to show 3 of those intervals in that statement so the reader gets an idea what the pattern is. If you choose not to put equal signs on your less than signs, you could alternatively write the same increasing intervals this way. Now, going back to what we said earlier, there's a whole discussion around how someone who wanted to show it more formally would do it. And in this case, what we're saying is if k is divisible by 2, in other words, if k over 2 is an integer, in other words, if k is an even number, then we can say that if you take the interval, give me any even number, let's say the number 4. If I go 4 minus 1 times 180 degrees, less than or equal to x, less than or equal to 4 times 180 degrees, I'll end up with 540 degrees less than or equal to x less than or equal to 720 degrees. And that would be right here. That would be kind of the next iteration of the increasing interval that we know is there. So the way we've described it here is a pretty nice formal way of describing those increasing intervals. Okay. So again, like we're saying here, k, when I say k over 2 is an element of the integers, I'm saying k has to be divisible by 2. In other words, k is an even number. So we're about to show you the formal way of writing this out using k values of -2, 0, and 2. So using k values of k value of -2, we would get this increasing interval right here. Using a k value of 0, we would get this increasing interval right here. And using a k value of 2, we would get this increasing interval right here. Okay? We could replace those less than or equal to signs with less than signs. In interval notation, we could write it, write the increasing intervals the simple way, like this, or we could write it more formally as shown. We could put all of those into radian mode by converting degree measures with radian measures. Remember to replace 180 degrees with pi in all of the descriptions. Now, similarly, looking at decreasing intervals, we go through a similar process, or we can state it more formally. And again, we're at the end when we say k over 2 is an element of z, we're saying that if we divide k by 2, we have an integer. In other words, we're talking about numbers divisible by 2, or in other words, even numbers, letting k equal those even numbers. And we see that if we let k equal -2, we get the decreasing interval from -360 to 180. If we let k equal 0, we get the decreasing interval from 0 to 180. And if we let k equal 2, we get the decreasing interval from 360 to 540. We could replace the less than or equal to signs with less than signs, although I don't like that. Your textbook accepts it, so I would accept it too. In interval notation, we write it using round brackets, or preferably for me, square brackets. Or more formally, we could state it using k's the way I've been describing. And if you're a computer science person, you might enjoy that. We could put all of those into radian mode, and we would do that by replacing 180 degrees with pi in all of the formal descriptions. Now, interestingly, this is an even function. Look at the first interval. If I take that iteration of the cos curve and I reflect it in the y-axis, I get this iteration of the cos curve. It's actually even. It's a periodic function that varies between -1 and 1 infinitely in both directions. So I can't say y is going to infinity or to negative infinity, and I can't pin down a value to which y is going. So I say there's no discernible end behaviors.